Good afternoon. This is our group's project about single crystal growth method. My name is Cherry Salumbides and I will be guiding you to our short video regarding our topic. The actors in this video are myself, Andrew, Neon, and Bing. The global market for gallium arsenide is expected to grow by as much as 15% during the forecast period of 2021 to 2026. This is primarily due to the increasing demand of gallium arsenide wafers over silicon because of better functionality, scalability, and compatibility to the developing market infrastructure. Gallium arsenide crystals can be created through different methods, and today we will review the common methods and their important effects on the resulting crystal properties. We have an investor here who is the CEO of Future Devices Incorporated, Ms. Bing Jamisola. Hi, Ms. Bing, and welcome to our Technology Hub.
Thank you, Che. I'd like to ask if you can help me discern where should I invest?
Absolutely. What do you want to learn?
I need to know about growing gallium arsenide.
Let's see, what do you want from your GaAs investment?
Well, I want the following for my first fabrication plant for gallium arsenide manufacturing. I need to know the throughput, if it is cost effective, there's an ease of manufacturing, is it suitable for devices, and it should be well established.
So first, let's have a short review of what are GaAs semiconductors. Gallium arsenide is a compound built from the elements gallium and arsenic. It is often referred to as 3,5 compound because gallium and arsenic are in the 3 group and the 5 group of the periodic table, respectively. Gallium arsenide is the material of choice for use in optoelectronic devices and circuits since silicon is such a poor light emitter. It was the optoelectronic applications, especially high-powered lasers and LEDs, that drove the materials and device development of GaAs for the first 2 decades. While silicon-based technology has been the backbone substance of the microelectronics revolution, gallium arsenide circuitry operates at the higher frequencies and signal amplification powers. Gallium arsenide is a compound semiconductor with a combination of different properties. So here are some of the important properties of gallium arsenide semiconductors. Based from the comparison of various structural and electronic properties, the advantages of gallium arsenide over silicon can be readily ascertained. Unfortunately, the many desirable properties of gallium arsenide are offset to a great extent by a number of undesirable properties. This limited the application of gallium arsenide devices to date. Then, let's visit my colleagues and see for ourselves which can fit your needs. Hi, Andrew.
Oh, hi. What brings you here?
I want to know more about LEC. Can you help me?
Sure.
Okay, I will leave the two of you to discuss about it.
Let me first explain to you what is LEC and its general process. LEC is the most widely used growth method for commercial gallium arsenide single crystal. Growth takes place in a water-cooled pressure vessel for pressure up to about 100 bar. It houses a pretreated reusable charged pyrolytic boron nitride crucible that is surrounded by a furnace including heat insulation. The gallium arsenide melt is covered with boric oxide, which is viscous and unreactive. This allows an overpressure of inert gas to be applied so as to contain the melt that is important for gallium arsenide and volatile components. For the electrical properties, a typical EL2 topographs for LEC and VGF GaAs are shown here. Mesoscopic distribution of EL2 and resistivity is usually measured by IR absorption measurements and contactless TDCM method. EL2 concentration is enhanced with better mesoscopic homogeneity and is due to an interaction of defects with dislocation as can be seen in the LEC topographs. The larger cell size of VGF GaAs is clearly visible, With smaller cell size, the average EL2 concentration is higher in semi-insulating LEC grown GaAs compared to VGF grown GaAs. As can be concluded from the mesoscopic EL2 distribution, the mesoscopic homogeneity of the resistivity is higher for LEC compared to VGF material. EL2 and carbon concentrations determine the carrier concentration in semi-insulating gallium arsenide and thus influences electrical resistivity. Shown here is the energy level positions of important dopants along with the energy level of the intrinsic defect, that is the mid-gap double donor EL2. And also, the arsenic anti-site defect is known to be the source of EL2. For LEC method, it has also a good control for carbon concentration that is important for a semi-insulating property. To achieve stable semi-insulating behavior, that is gallium arsenide with high electrical resistivity, the following mechanism is utilized. First, there are both N and P-type unintended impurities like silicon or zinc. Second, to compensate the donors, a shallow acceptor is requested. The preferred one is carbon. Third, under this condition, the deep level EL2 defect can compensate the acceptor. The requirements for semi-insulating behavior can be described following the simplified compensation model. EL2 is greater than acceptor minus donor. So, must be greater than 0. So, in this explanation, we can see the importance of the mid-gap double donor EL2 and the carbon. And again, LEC method has a good control of this. In terms of manufacturability, LEC method developed history. It has a good crystal form factor. The PBN crucible is up to 14 inches diameter, can charge up to 50 kg, and thus used to grow semi-insulating GaAs single crystal up to 200 mm. Also, more than 300 wafers can be produced. Fastest growth rate and good for mass production. Single crystalline yield and the structural quality of crystals are lower if growth is performed with a working point in the turbulent region. LEC growth of large diameter gallium arsenide crystals already takes place beyond the borderline in the stationary turbulent regime, as shown in this diagram. Height of the melt cannot be further enhanced, and therefore, the diameter of the crucible and the related dimension of the hot zone of the LEC puller have to be enlarged to grow longer crystals. For the mechanical properties, LEC method have high dislocation density due to high thermal stresses at its growth plane and high thermoplastic relaxations, higher even at the boundaries of growth ingot. Grain sizes are smaller, typically better mechanical properties due to low dislocation propagation because of its high dislocation density. For the summary, in terms of manufacturability, it has well-established equipment and technology, reliable and fast growth method. However, it has a difficult thermal field controls. In terms of product quality, it has mesoscopic homogeneity. It has a good controlled carbon content. It has a strong mechanical properties. It has a very good semi-insulating properties. However, it has a high dislocation density. The typical application of LEC grown gallium arsenide is for MESFETs and RF transistors, which are presently in demand in the market today.
Oh wow! I learned a lot. But I still have a few questions.
Sure, far away.
Seems you enjoyed a lot, Miss B.
Definitely.
Now let's go and meet my pal on the Bridgman methods.
Ernest.
Long time no see, Neon.
Hello there.
Hi!
We were thinking if you can help Miss Being here to learn more about your process.
What about?
Maybe we can start with how Bridgman methods work.
Okay, in this company, we use two kinds of Bridgman method to grow gallium arsenide. First is the vertical Bridgman or the VB method, and the second is the vertical gradient freezing or the VGF. VB and VGF methods are Bridgman techniques that move molten material across a hot zone to a cold zone to grow a crystal. What you see here in the diagram on the right is an arsenide-rich gallium arsenide melt in PBN crucible. At the bottom end of this crucible is a seed where crystallization starts to take place. Now this crucible is slowly lowered through a temperature gradient across the crystallization temperature of gallium arsenide. There are certain controls in place in order to keep the surrounding temperatures in check. Lastly, it is also important that the solidification or the crystallization temperature is gradual across this movement to ensure low formation of dislocations in the crystal. The vertical Bridgman or the classical Bridgman is quite similar to that of the vertical gradient freeze method. Both methods utilize the same concept that I described earlier, in which both conditions need to move across a temperature gradient. The only difference is that the vertical Bridgman utilizes the crystal carriage movement or the entire assembly moving along the z-axis, whereas on the vertical gradient freeze, there are computers that control the temperature fields in order to simulate the movement. In both methods, due to the gradual change in temperature, gallium arsenide crystals solidify slowly as well. This results to larger grain or cell sizes of the crystals that affect the mechanical properties entirely. With controlled temperature environments, there are less variations to the temperatures that will result to a low dislocation density crystal. Similar to LEC, von Mises stresses for Bridgman-grown crystals are still higher towards the periphery, but due to its larger grain size, it's still less than that of the LEC method. There are some drawbacks, however, for our processes. Arsenide can still precipitate readily as the crystal solidifies and settle in the dislocation sites. These cause precipitate dislocation sites that can be unwanted for high-end devices. What you see here below are higher shear stresses at the red zones for VB going up to the center of the ingot, whereas LEC has far less shear stress sites. However, this can be easily resolved simply by annealing the crystal. We now move on towards its electric properties. Grain sizes and the method of growth affect these properties as well. Having low dislocations and large grain sizes typically result to good electronic properties. The diagrams below show a comparison with LEC and VGF methods, where there is a lower EL2 defect density for VGF. Because of the temperature controls in place, arsenide source is well maintained, allowing the use for semiconducting or low-resistance devices such as photovoltaics or photonics. We do acknowledge, however, that there can still be some impurities from the system that cause deposits with gallium arsenide, and that is carbon. For gallium arsenide manufacturing, it is a fairly easy process. Since the whole ampule is moved for VB method, we're considering VGF method to be stationary with only temperature fields being changed, then there is hardly a problem for mechanical parts. The GaAs polycrystals are fed into one location of the ampule and is lowered to form the melt and the single crystal. It only requires one feed-through, unlike LEC, which requires two pulling rods. The end product is also reliably consistent in a cylindrical shape, which you can see in the images on the right, which states better product uniformity than LEC. The reason behind is that the temperature gradient is antiparallel to the pull of gravity and its movement. This results to less thermal convections that may affect the crystallization temperatures experienced at various parts of the ingot found in long melts. This makes VB and VGF methods to be less costly in terms of investment and operating expenses for large-scale manufacturing. The downside is the throughput is lower due to the precise control of the temperature gradient. This also affects the pull speed, limiting both methods to a maximum growth rate of about 1 to 3 mm per hour. We can speed things up a bit, but this will affect the dislocation densities and will be economically costly versus LEC. Furthermore, there is a surprise in every ingot pull. There are hardly any visual controls or indicators as the ampule is lowered in the system, so to see if the crystals have already some defects or deformation, it will be hard to abort the run and have to reload the process. To mitigate these, there are some methods being employed by our R&D team to make use of magnetic fields to further control the temperature gradient and thus the crystal growth in the system. In summary, VB and VGF methods are very similar with each other, except for their manner of cooling or solidifying gallium arsenide. This results to overall low capital expenses and good quality product, however at the expense of throughput. Both methods, when compared to LEC, are mostly influenced by the grain or cell sizes. It results to low EL2 defects and low residual strains, forming a good candidate for high-end electronic products. We do have to keep in mind to control the impurities such as carbon and arsenide precipitates by annealing the grown crystal, which adds to lower productivity for these methods. But considering that the future will start to shift towards gallium arsenide devices, both VB and VGF methods seem good techniques to cater the increasing demand.
So, let me clarify some things.
Busy as always. Anyway, I think VB, VGF methods need a lot of attention in order to be productive. Let's go back and summarize what you got.
Correct.
Thank you for your time.
Now let's list down the pros and the cons for each. Can you share what you have learned so far?
Yes, here's what I got. The LEC and BV and BGF method in terms of impurities are on the same level. LEC have high dislocation density and carbon control. Its crystal length and diameter are fairly suitable, as well its manufacturability. And this method are already established. While the BV or BGF method primary advantages is its low cost, low investment, and low operational cost. For the applications, the LEC are more suitable to FETs, micro devices, and implantation. Then the BV-BGF methods are for LEDs, photonics, and PBs.
For my present investment, I think I'll go for LEC method, since this is suitable investment for large-scale production. This is to cope up for the present-day demands. And moving forward, my company will adopt the BV or BGF method as it's very promising, easy to manufacture, and cost-effective.
Thank you so much, TechnoHub team, in explaining and giving me so much information. Really, you guys are all experts in your field. Again, thank you for your time and effort. I know now on where to invest.